Picture this. You're an astronaut, adrift in deep space, and you throw a rock as hard as you can. According to Newton, that rock should keep gliding forever, right? But it doesn't. It slows down, and eventually, it just stops. Wait, where did the energy go? This isn't a sci-fi riddle. It's one of the most shocking misconceptions in physics, and for over a century, even Einstein wrestled with the answer. In school, we all learned this golden rule of physics that energy cannot be created or destroyed, only transformed. Whether it's a swinging pendulum or a rocket launching, energy simply swaps forms. In fact, classical physics made this seem like the Holy Grail. A law as rigid as gravity itself. But there's a twist. That law works perfectly until you zoom out, way out, to cosmic scales. Because in the language of Einstein and the reality of space-time, energy conservation is no longer guaranteed. But why? Because the universe itself is evolving. And with it, the rules bend. Let's now get back to 1915. Einstein stood at the University of Göttingen, lecturing on a theory that would change science forever. Yeah, you got that right. The theory of general relativity. But there was a catch. Einstein had not yet figured out how to show energy conservation in his theory. You see, in Newton's world, gravity was a force. In Einstein's, it was the curvature of space-time itself. So, where was the energy hiding? Was it in the curvature? The stress-energy tensor? Even the mathematical genius David Hilbert tried his hand, and the best he could do? A set of equations called the Bianchi identities. They proved energy conservation, but only in an empty universe. In ours, it's anything but empty. Enter Emmy Noether, a name you've probably never heard, yet she's been called the most significant creative mathematical genius since the higher education of women began. Albert Einstein, born in an era where women were literally banned from universities, Noether wasn't even allowed to enroll. Yet, she persisted, auditing classes, earning her PhD, and eventually becoming a pioneer in abstract symmetry. And when Hilbert was stumped, he turned to his assistant, none other than Emmy Noether, and what she discovered would shake physics to its core. Symmetry equals conservation, the secret behind every law. Let's talk symmetry now. Not just pretty triangles, deep mathematical symmetry. What if I told you that every conservation law, momentum, angular momentum, even energy, is a direct result of symmetry? That's Noether's first theorem. And here's how it works. Move an experiment across space. If physics stays the same, that spatial symmetry momentum is conserved. Rotate an experiment. If the outcome's unchanged, that's rotational symmetry angular momentum is conserved. Run an experiment tomorrow instead of today. If results match, that's time symmetry energy is conserved. This wasn't just theory, it was a revelation. For the first time, physicists had got to know why conservation laws existed. Well, time symmetry only works if the universe behaves the same today as it did yesterday. Spoiler, it doesn't. Since the 1920s, astronomers have known galaxies are flying apart. In fact, the farther a galaxy is from us, the faster it's speeding away, a discovery by Edwin Hubble that revealed. Then, in the 1990s, scientists studying supernovae made an even bigger discovery that the expansion is accelerating. Translation: the universe is not symmetric in time. It was denser, hotter, and smaller 13 billion years ago. It'll be different billions of years from now. And without time symmetry, energy conservation just breaks down. All right, time for a mind blower for you guys. Photons released 380,000 years after the Big Bang, part of the cosmic microwave background, have been traveling through space ever since. In fact, they started out as visible light. And now? They're microwaves. They've lost 99.9% of their energy. But where did the energy go? Nowhere. It wasn't converted. It wasn't transferred. It simply disappeared. Let me remind you here, that doesn't break any law. Because in our time-evolving universe, there is no law that demands energy be conserved. Yeah, you heard that right. Noether didn't just wave her wand and declare it. She proved it, using something called the principle of least action. In physics, everything takes the path that minimizes action, a quantity involving energy over time. When the laws of physics are invariant under shifts in time, this principle yields energy conservation. But the moment that symmetry disappears, like in our expanding universe, that guarantee vanishes. Mathematically talking, it's airtight. Symmetry equals conservation. No symmetry equals no conservation. And this brings us to something even deeper. Einstein, in trying to conserve energy in general relativity, proposed an equation. But Noether saw the flaw. It relied on a pseudo-tensor. Now, what's that? A pseudo-tensor doesn't behave well under a change of reference frame. It doesn't transform properly, unlike real tensors. So, depending on your perspective, gravitational energy could vanish. That violated general covariance, the very backbone of general relativity. So, you see, Einstein's attempt was, quite literally, not tensor enough for this universe. On the other hand, Noether didn't stop at one theorem. Her second theorem tackled local symmetries, like general covariance. She discovered something else. Even when global conservation fails, we can still track energy in small regions, thanks to something called the continuity equation. Just picture pipes of water. If water enters one section and exits another, the amount changes only if there's a leak. Similarly, in space-time, local patches of the universe do respect conservation laws. But across billions of light years, the curvature of space-time, the very shape of reality, acts like those leaks in the pipe. So, my dear fellas, energy doesn't get destroyed. It just leaks into the geometry of the universe itself. Wait, there's more. Noether's impact didn't end with gravity. In the 20th century, physicists realized that symmetries define everything, including the forces of nature. Thanks to her ideas, electric charge conservation comes from gauge symmetry, the standard model, built on Noether's framework, discovery of quarks, the Higgs boson, and even attempts at a theory of everything, all owe a debt to her theorems. Not bad for someone who once wasn't allowed in a university classroom. What do you people think? Did you know? Noether continued teaching in her kitchen even after being banned by the Nazis. One day, a student showed up in full Nazi uniform. She taught him anyway. That's how much she loved math. The Higgs field, responsible for giving particles mass, emerges from symmetry breaking, a concept inspired directly by Noether's ideas. In 1935, Einstein said of her work, "It is hard to believe that such a significant mathematical contribution was made by a woman during such a time." Back to the topic. So, if energy isn't conserved, why does it usually seem like it is? Because in the short timescales we live in, the universe barely changes. The expansion is slow. So, for most experiments, time symmetry still holds, approximately. Putting it simply, conservation of energy is an incredibly useful illusion, but an illusion nonetheless. Just zoom out far enough in time, and that illusion breaks. In the ever-expanding tapestry of the cosmos, not even energy gets to stay the same. The only constant could be our quest to understand. So, if this shattered what you thought you knew about physics, well, hit subscribe, thumbs up, drop a like, speech balloon, and tell us in the comments, what other truths in science do you want us to unravel next? Because in space, nothing is truly conserved, especially not your old physics textbook.